We're going to work through an example where we linearize an energy balance. In this case, it's for this thermocouple right here, a little bead that's sitting at the end of two wires that are twisted together. And this is going to be our thermocouple temperature right here, T sub T. And we're going to do an energy balance right around this little bead right here to determine what the temperature is going to be reading. Now our gas temperature is going to be changing throughout this system. Some advanced combustion systems operate in this pulse mode where an acoustic wave resonates in this combustor. In order to enhance the heat mass transfer, the frequency of the wave is approximately 100 hertz, so 100 cycles per second. And as a result, the temperature at any given spatial location, okay, so here or here, may fluctuate with a sine wave or cosine wave with an amplitude of 75 degrees C. And so we want to develop an energy balance around this, linearize it, and see how well that linearization, the linearized differential equation, fits the nonlinear differential equation. And you can see just an initial simulation of this. This is the gas temperature right here. And this is the nonlinear simulation of the thermocouple temperature. So you can see that it lags the oscillation by a little bit, okay, and only fluctuates maybe 5 degrees Kelvin, whereas the gas temperature is fluctuating at a much higher level. So we're not really measuring the true gas temperature because the thermocouple is not small enough to be able to respond to that. Now, what you could do is there's a question here, a thought question, and so we want to say what changes could be made to the thermocouple to improve the ability to measure the gas temperature. So we have all of this information about the heat transfer coefficient, the density of the thermocouple, the Stefan-Boltzmann constant, the emissivity, Stefan-Boltzmann emissivity, the steady state temperature for the thermocouple, steady state temperature for the flame, the heat capacity for the thermocouple, and the diameter of the thermocouple. So we have all that information, and let's go ahead and start developing this energy balance. So we're going to have the enthalpy of our thermocouple, and then it's going to have a couple different terms here. We're going to have convection, we're going to have radiation, and we're going to assume that the conduction is negligible in this case. So you could have some conduction, temperature differential here along the, along these wires, but we're going to just assume that's negligible for now. Okay, so we just have the convection from the gas, and then we have radiation from the flame as well. So let's put together this energy balance. Okay, we have the in minus out, so we just look at all of our energy terms and we just put that in terms of the in minus out value. So I'm going to say this is going to be my heat transfer coefficient. I'll say this is maybe the UA value, okay, times temperature of gas minus temperature of the thermocouple. And I think down here I actually said that was an H, like this this overall this heat transfer coefficient. So let's just change that to U instead. Okay, so UA. Okay, so this is my convection right here, my my energy that's being transferred into or out of this thermocouple bead due to a difference in gas temperature and the thermocouple temperature. And then I also have to put in my radiative heat transfer as well. And so that's going to be the area, the surface area, times the emissivity, times the Stefan-Boltzmann constant, times the temperature to the fourth of the flame minus temperature of the thermocouple to the fourth. So one of the things is I sometimes mess up the signs here, which one's positive, which one's negative, here and here. So one of the things I like to do when I'm thinking about this is, I look at the accumulation term here. So if it has a positive slope, it's going to get hotter. So if my gas temperature is greater than the thermocouple temperature, we know that the temperature of the thermocouple is going to increase. Okay, and so we say that we have a positive slope. So those signs are correct. And then if we also have a flame temperature greater than the thermocouple temperature, then we also know that the thermocouple temperature is going to increase, so we have a positive slope there. So I typically write these, do that little thought experiment, make sure I have my correct signs there, and then move on. So to do the linearization, we're just going to apply this is going to be a function of a couple of variables. We have our thermocouple temperature, our gas temperature, and our flame temperature. Okay, those can all change. In this case, just the gas temperature is going to change, but let's go ahead and linearize with respect to the flame temperature as well. And so that's going to be equal to, and then I'm going to plug in the steady state conditions. And there I go, I have the steady state conditions. And then I take the partial derivative of f with respect to the thermocouple temperature, plug in the steady state conditions, and then do temperature thermocouple minus temperature thermocouple initial. Okay, and then I do that for the other ones as well. The partial with respect to the gas temperature, and there I have the next one, and then the final one, which is going to be the flame temperature. Now in this case it doesn't change, but you could always linearize with respect to it, and then just say it doesn't change from the initial values. So then it would be a 0 value here. Okay, and we just want to calculate the partials here. If we choose steady state initial condition, or the steady state conditions, and this is going to be equal to 0. So a lot of times you can just throw that out just by saying if steady state conditions, and that just makes dHt dt equal to 0. So that's a very nice thing. We just throw out that term. Okay, if only if we choose steady state conditions. Okay, let's go ahead and calculate these these partial derivatives here. I'm going to call this one right here. Let's just go ahead and call this we'll call this one alpha, and we'll just call this one beta. Okay, we'll call that one beta. And then, okay, we can call this one like gamma. Yeah, these are all just going to be constants in the end. Okay, and when we linearize that, we linearize this expression, we just take the partial with respect to the this thermocouple temperature. And so let's just do that one. Alpha equals, and that's just going to be equal to UA. Okay, and then let's see, that is it. Negative UA. Okay, and that was from this term right here, and then I need to do it on the other one as well. And so that's going to be negative 4 times A times emissivity times Stefan-Boltzmann constant times temperature T naught to the third. So here's our constant. It's right there. It's just going to be equal to a number. Let's calculate beta now. Beta is just going to be the gas temperature, and that's just going to be equal to UA. Okay, so that was pretty easy. There we have our linear differential equation. The one thing that we do need to do, though, is we need to relate this to temperature, not just to enthalpy. And so let's go ahead and just make that, let's just go ahead and break that down into the M of mass of the thermocouple times the heat capacity of the thermocouple, and then we'll have D temperature of the thermocouple minus our reference temperature, which is going to be constant, and so that's just going to be M. Okay, M C sub P dt thermocouple D times. So we can just plug this in right up here. Okay, then if we Let's go ahead and just do m c sub p d thermocouple d time equals, and then I'm going to have my alpha times temperature thermocouple minus temperature thermocouple not, plus beta times temperature of the gas minus temperature gas not. Okay, and then you could have the gamma here as well, flame minus flame not, but we're just going to say that doesn't change. Okay, there's my linear differential equation. Now I want to be able to simulate it and compare it to this nonlinear response and see how good of an agreement I get to the red line. So to do this, I don't necessarily recommend starting from scratch on this, especially if you don't know how to, if you're not feeling comfortable with the simulating these differential equations, but you could plug in this differential equation and solve it with ODE int. If you need to start from a starting place, then just come to the course website /APMonitor.com/PDC, and this is under assignments, and this is under linear simulation. So this is exercise number 2 on the thermocouple, and there's all the information, and then if you click show solution help, you can see that plot. And if you come all the way down here, just go ahead and grab the code. It will download it for you. You can save it somewhere like your desktop and then begin to edit it. You can do that with Spider or with IDLE or with Jupyter Notebook. Any of those will work. So let's just go ahead and run this one first and see what it gives us. Okay, there's our plot that we had before. And I'll go ahead and put this console over here. Okay, so we want to add the linear simulation now. I have it set up here where it says tlin equals x1. And then a little bit here where you say add linearized expression or linearized equation here. Let's just go ahead and do this within this function, this one function. You could break it out into 2 functions if you wanted to and simulate those independently. But because I have a lot of these constants and other things here, I'll just go ahead and do it in one. Okay, so we're just going to be calculating the 2 differential equations together. Here's our nonlinear one right here that came from the convection term and the radiative heat transfer term, and then we're just simulating the derivative of temperature with respect to time, and just the combination of those 2, and I divided it by the mc sub p. Now mass is equal to the rho, the density, times the volume, and I also had calculated that up there as well. Okay, so let's go ahead and add the linear model. We're just going to add in the initial steady state values. Okay, so this is going to be 1500 for all of them. Flame temperature, for the thermocouple temperature, and the gas temperature. Those are all at 1500 degrees Kelvin. Okay, and then I'm going to have this term on the left. That's going to be my denominator. Let me go ahead and bring this up just so you can see this at the same time. And okay, let's get my alpha and my beta values here. Okay, so I have the very first one is going to be this denominator that I'm going to divide over, which is the mc sub p, and that's just going to be equal to the rho times the volume times c sub p. And then I'm going to have my alpha value, and my alpha value is going to be, let's see, it's going to be minus h. I guess I did say this is h here. I got rid of enthalpy, so let's just leave it as h watts per meter squared Kelvin times a time minus 4 times t thermocouple to the third power times area times epsilon times sigma. Okay, and then all of that I need to divide it by what was on the other side. Let's see, this just need to divide out mc sub p on both sides, m c sub p, and the mass is equal to the density times the volume. Okay, so let's see, where am I here? I need to do another parenthesis just for alpha, and then divided by this denominator. Okay, denominator. Okay, let's do the beta now. The beta is going to be equal to the h times a divided by denominator. Okay, and then I could also do the gamma if I wanted to. I'll just skip that for now. Let's do the linear. Okay, the derivative here is going to be alpha times, in this case, it's going to be T linear minus T thermocouple naught plus beta times T, let's see, what is this going to be? T gas minus T gas naught. Okay, so we have our linear and our nonlinear. Okay, I have my initial conditions there. Both of them are going to be at 1500 Kelvin. And then I'm going to simulate for 1,000 seconds with 0.1 intervals. And let's see, there's my flame temperature right there. That one is 1520. Okay, I did change it to 1520 in the flame temperature. Oh, rats, I need to go back and do gamma. Okay, so let's just put that one in there. I'm going to linearize with respect to gamma, or with respect to the flame temperature as well, because I did have to do a step in the flame temperature. So that one's pretty easy. It's very similar to what you just saw before. Let's just go ahead and do that. Okay, gamma. Okay, flame temperature. Okay, where am I? Right here. I'm just going to do this. Okay, those are the terms that have the flame temperature in them, and so gamma is going to be equal to 4 times area times epsilon times sigma times flame temperature naught to the third. Okay, so there's my gamma value. All right, and then I have to divide it by that denominator as well. So 4 times flame temperature to the third, and then times area times epsilon times sigma, and I'll put the parentheses around it and divide it by that denominator. Okay, and then add the gamma times flame temperature minus flame temperature naught. Okay, there I go. So I was trying to be lazy before, but then I realized that I needed to actually add that in. So we just added that additional term because we do have a step in the flame temperature right here. And we need to be able to have the linear equation understand what is the effect by that flame temperature. And so we just included that additional linear term there. Okay, and then we have the gas temperature, which is going to be the flame temperature plus that, it's going to be that oscillating value. Okay, and then we store the linear and the nonlinear temperatures there. We're going to run through this and just store them and then plot them. And let's just add the linear thermocouple temperature here. Just going to copy this and then add T lin, and let's go ahead and make this one a black dashed line, and we'll just call this one linear. Okay, now whenever I run this the first time, it seems to always have an error, so let's just see where our first error is, and then we'll look at the debug and go from there. Very few times I'm actually able to get it correctly the first time. Okay, so C sub P is not defined. Okay, that just says, I had capital C sub P here, but I used a lowercase C sub P down here somewhere. Okay, I think that's in my denominator. and actually pointed to the line there, line 34. Okay, let's do this again. See where the next error is. Oh wow, okay, so that came out. Okay, so we have the nonlinear, which is in red, and then we have the linear. So you can see if there's a step in the flame and gas temperature. You can see it oscillating up here. There's a step, the gas temperature change, the flame temperature change, and so you can see the response of this thermocouple, that it is measuring, if there's a sudden change, it does not measure right away. It takes 0.05 seconds even to get up here just a little bit further. Okay, so what could we do to this to improve the sensitivity of the thermocouple to the actual temperatures? So let's do this in simulation because we have the linear and the nonlinear here. One idea is to increase the heat transfer coefficient somehow. I'm not sure how you would do that, but let's just go up to 4800 instead of 2800, and let's see if it's any faster. Okay, so it goes up just a little bit faster. If you were able to put fins on that or something like that, you might be able to get that temperature up there, be a little bit more responsive. Let's also, so I'm going to set that back to the original. Let's say I decreased by half that thermocouple bead size, so I made it smaller. Let's see what this would do. Okay, that also helps. Let's just really start decreasing this thermocouple bead size. I'm going to do it by an order of magnitude. So it's going to decrease the area, but you can see it's also going to decrease that mass of bead that you need to heat up or cool down very fast. You can see it becomes more sensitive. So let's see how far we would have to take this before you're really measuring the actual gas temperature. Okay, so we're getting much closer there. Okay, but if you have it that small, you could have some concerns about the it actually conduction might factor in there. There's some other things. It's just a simulation based on our assumptions that we made, but there's some things that you can do, like reduce the diameter of it. You could increase the heat transfer coefficient in some ways, or you could even decrease the heat capacity. For example, use a different material there for the bead that has a lower heat capacity. I don't know what 0.1 would be, but that would also help it as well. Okay, so there we go. We have this solution.